All right, everybody, let's continue on talking about the chi-square. We just wrapped up doing the test of independence. So in this video, we're going to cover the second kind of chi-square called the goodness of fit test. Now, the goodness of fit has all the same basics of the chi-square that we covered in the test of independence section. So I'm not going to review those here, but just know the goodness of fit test is still a chi-square fundamentally. So it has all those basics the same as the test of independence. So let's just jump right into the goodness of fit test and how it works. So let's start with talking about the what and the when. Okay, what is it and when do you use it? So the chi-square goodness of fit test is when you want to look for a significant difference between what you observed and what you expected to find. The goodness of fit test is essentially kind of like the most bare bones basic chi-square, because that's essentially what a chi-square does, just like the test of independence. It compares observed to expected data. The test of independence is comparing observed and expected data to each other to see if they're different, so you can determine if two variables are related or not. The chi-square goodness of fit test is simply interested in if observed data is different from expected data, just period. Okay. Now, the thing about the goodness of fit test is that there are two different assumptions for finding your expected data. So you would find your expected data depending on which assumption you're going with. So the first assumption is that if you expect your groups to be equally distributed, then that's how you find your expected data, right? If you have a total of 100 people and 5 different groups, and the assumption is that, well, the groups are equally distributed. So out of 100 people, you would expect under assumption 1 that 20 people would be in each group. So that's the first assumption. The second assumption is that the groups would follow a specific distribution. Let's say that you expect there to be a certain amount in one group, a lesser amount in the second, a greater amount in the third, and so on, right? So it's not equal across. It's that, oh, there's a specific amount in each group. And then you compare the observed to that expectation. So you got to focus on which assumption is there. Now, the assumption is usually determined by some type of theoretical basis, right? A researcher has some reason to go with one assumption or the other. So I've made that clear in the assessments of which assumption that you should follow. So when you get to doing a chi-square goodness of fit test, it will be clear to you in the scenario and the description of for that test that you're working with, which assumption that you need to utilize. Now, when do you use it? Same situation you would use any chi-square. You got nominal categorical data from one sample. You're comparing observed to expected. With the goodness of fit test, you only have one variable, though. Test of independence, you got 2 variables, right? Because you want to see if they're independent of each other. Goodness of fit, you only have 1 variable, right? So just keep that one in mind. So let's work with a question. Let's put this in the context of a question we could ask. So let's say that we have this general question, a curiosity for candy lovers. Do M&M's packages follow M&M's theory about their candy's color amounts? M&M's claims to have a certain distribution that they theorize every single one of their packages should have, of how many of each color of M&M's should be in the package. So we want to know, does M&M's theory about their candy's color amounts, does that actually line up with the actual color amounts you would find in a package of M&M's? So that was our general question. So how do we make it more specific? So the research question is a little wordy here, and that's just the nature of the goodness of fit test. So pay close attention to how the sentence is structured. So the research question asks, is there a significant difference between the observed M&M color proportions and M&M's expected color proportions? Okay. So it's looking at, is there a difference, right? So we want to compare, that's our comparison there, between the observed and whatever the variable is, and then the expected and whatever the variable is. So the variable is listed twice, one in the observed, one with the expected, right? Because we have an observation with our variable, and then we have the expectation with our variable. So let me highlight these things that we just talked about. So one, that you're dealing with nominal or frequency data. Again, usually that's going to be more clarified when you actually look at the data, but a key word, if you see in the question, is proportions. That means you're dealing with nominal frequency data. but you often won't see this in the general question. So you'd have to look at the data to know if you're working with nominal data. And if you are, you might want to use the word proportion in your research question because that indicates frequency data. Now, of course, when you're comparing observed to expected data, that's clearly a chi-square, and it's specifically going to indicate chi-square goodness of fit test, right? The test of independence chi-square, the research question is worded differently than this. Now, remember, the expectation is assuming equally distributed groups or assuming a specific distribution of data. So you just need to make sure that when you calculate your expected values, that you have to do it according to which assumption you need to use moving forward. So what are our variables? Well, we got a single x variable, and that's going to be indicated in our research question. So our x variable is simply M&M color proportions, right? We have what's observed and we have what is expected. Now, how is this one? So with the variable here, a good thing to do with a goodness of fit test is to look at what is the expectation that you're going with? What's the assumption that you're going with for the expectation? Now, we know that M&M's, the company, has a theory about what their M&M color proportion should be. And their theory is not that there's an equal amount of each color. Their theory is that there's a specific amount of each color in every package of M&Ms. So the assumption we're going with is assumption number 2, that the groups are going to follow a specific distribution. Okay? So let's start to tie this together. Let's put some context here. So let's say that one Friday night, because you just have nothing better to do, you go and buy 4 1-pound bags of M&Ms, and you decide to just dump them all on your coffee table, and you separate them by color and count out how many of each color that there are. What a fun Friday evening, right? So you counted a total of 2,081 M&Ms. And this is assuming you did not eat any on the way. Okay, so 2,081 M&Ms total from 4 1-pound bags. And then you can see the distributions of the color. Brown seems to be the most with around 600, red and yellow towards the 400 and in the upper 300s, and then blue, orange, and green all around in the 200s range. Now, M&M's theory is that 30% of M&M should be brown, 20% red and yellow respectively, and then 10% blue, orange, and green respectively. So now what we want to know is the amount of M&Ms that we counted up, right, is our sample of M&Ms that we see here and the distributions of the colors in each category, does that match up with M&M's theory, with their specific distribution of colors they've talked about here? So here is how we calculate the chi-square. The chi-square score is calculated the same way you learn in the test of independence. The expected value is calculated differently, okay? That's the thing that you need to make sure that you have distinguished. Expected, the E's, are calculated different for the test of independence than they are for the goodness of fit test, okay? So the goodness of fit test, the way that you calculate this is you take the observed frequency and you multiply it by the expected proportion. Okay, so we took our percentages from M&M's theory, we turned them into decimals because that's how you more properly work with them. So if I wanted to calculate the expected frequency, what is the amount of brown I would expect? And then I would take the total amount, 2,081, and I would multiply it by 30. Because out of 2,081, if M&M's theory is correct, 30% should be brown. So I multiply 2,081 by 0.30. And that's how I get my expected frequency. And you're going to want to do that with each each category there. Pause the video, calculate those expected frequencies. Now to compare to see if what you got, if you were on the right track, this is what you should have gotten. So this is the expected frequencies here for brown, red, and all the other colors. Take a second and compare what you actually counted up compared to what you would have expected to count up. They're not identical, they're not the same, but there is some similarities. Brown's not too far, it's like 22 M&Ms difference, but some of them have quite a larger gap between them that you can see here. So we need to do an overall analysis, right? So let's take our differences and then finish off the calculated chi-square. Square the differences, divide them by the expected frequency, and then sum them all up. Pause the video, calculate that, and then keep on going. So here's what you should have gotten, okay? So we see our differences here. Just looking at absolute values, disregarding the negatives, which color category has the biggest difference between what you found and what you expected? Looks to be yellow, right? The difference there is about 37 M&Ms, the difference between what you found and what you expected. In fact, it's in the direction of there's 37 less yellow M&Ms than what M&Ms theorized you should have found out of 2,081 M&Ms. So we square that, we then divide it by E, and then we sum it all up, and we get a chi-square of 15.49. Now let's do a quick refresh of what the chi-square score is telling us. So remember, it represents the observed values and the expected values. The further the chi-square score is from 0, the more different O is from E, okay? This point here is repetitive from the test of independence here. So we're not working with two variables, so let's disregard that. In the goodness of fit test, the further the chi-square is from 0, the more different O is from E, which could indicate that then the data does not fit the theory, okay? The data does not fit the theory. So the observed color proportions not fitting M&M's expectation may account for a larger chi-square score. Now, a larger difference could also be due to sampling error. We could have just had a bad sample of M&Ms, or we just got 4 1-pound bags that just the machines did not separate the colors properly, right? Mechanical error, what have you. That could be a possibility. So it could be because what we observed does not fit the expectation, right? The data does not fit the theory. Or it could be because of a bad sample. So in our next video, we'll wrap up goodness of fit and how we can use it in the process of hypothesis testing.